Welcome to our compilers projects. This is the project of me, Anas, and then my two partners, Prem and Biamba. Um, to start off, you can see in front of you a bold script. This contains the standard command to just generate the antler generated files. The antler generated files are in the output map. As you can see, the lexer is present, the listener, the parser, and the visitor. Um, Next off, I'm gonna show our grammar. This grammar is not made by us. We have used the grammar that Antler itself provides. Uh, it contains everything we need to compile a subset of C, and this is what the grammar looks like. Next off, we will showcase our symbol table. To showcase our symbol table, we will run with this command. We can run one test file. It will compile its LLVM and its dot format of the tree, and then print out the symbol table. The symbol table will be explained by my teammate Pram.
Hi. The symbol table manages nested scopes of symbols and methods. How we have designed this is actually in two steps. First step is with the symbol type, which represents the variables and the symbol in a language. And we also get the type, whether they are assigned, if it is a constant and other things, which are needed for a variable and the registrar also. And the other thing is the methods or the function of the language itself. Uh, To write the symbol table, we have used stacks and list, which provides, it has different functionalities like to open scope and close scopes, and also to add symbols and add methods. This is the implementation of a small type. And as you can see, the variables are in different scope and the methods are in different scope of the symbol table.
Okay, so now that the symbol table has been explained, um, I will continue to showcase our AST. Our AST has been made by multiple tree nodes. It has one main class called the tree node, and then we have multiple subclasses called like compile unit node, argument definition node. Why have we done it this way? As you can see in the grammar, you also see compile unit, argument definition, just like the nodes we have made. We have chosen to use the listener pattern instead of the visitor pattern to compile make our AST. So with the help of the listener functions, like enter return statement, for example, we visit every a node in the CST and then transform this in our AST tree. Um, you can also see as the previously generated dot format tree, we have generated a, uh, a AST made from the test uh, test uh, test file C that is in our input. As you can see here, there's a test function, an include of studio age, and an int main that has an integer k, I, etc. And if we go to the dot format and zoom in, oh, you can see, for example, the int k is being detected and made by the tree, as well as for the int I and the addition that is being assigned to the int I. And you can see that the rest has also been defined here. For example, the test function, you can see it on the dot format as well. We have also added that you can see its actual value, so that is being assigned. So like 10 here is being compared to x right here. And if you see here the pointer that has been made in the function, you can also see the address that is being used for that pointer. We will also showcase the tests that have been provided by the teachers. Those are the advanced tests. Here's for the correct code, binary, etc. And there's like tests that should provide a semantic error. To showcase this feature, I will run the benchmark that we have made. It's in the benchmark.py. But if you run that with this command, that's also provided in the README. You can see everything. Oh, well, the symbol table print is still on. To make it a bit more clear, I will run it again without the symbol table. So, okay, you can see every file being compiled, and if we scroll up, all the way up, you see it starts with binary operations, then break and continue. If we open up these test files, you can see that everything in this file gets compiled, it finishes, and if it has an error or something is not right in that file, it will print it. Um, the same is for all the rest of these files. We also provided unused warnings. So if you go to float conversion.c, you can see that it says variable I and z are unused. And as you can see in the file, they are declared and defined, but they are not further used. So it will also give you a warning. And then if we scroll to the bottom to showcase some of the errors, we can go to semantic errors, the test files, and you see that variable redefinition 6.c has a redefinition of a variable, so it should print a semantic error. And if we go here, we can see that it is being done wrong, so it will also print a duplicate. We have more error detection, like variable x is undeclared, and if you go there, you can see that it is actually undeclared, so it's printing the correct error. And the same is done for the rest of the files that should provide semantic errors. Some of the files are not detected because our semantic analysis is not perfect, but in most cases it will detect if something is wrong. Okay. If you're asking where these semantic errors are being found or detected, they're mostly detected in our symbol table which has been made by Prem. It always detects if something has gone wrong. If you're asking where we can see these errors being printed, we have created a logger that that uses our grammar error listener, which is also an Antler provided class, and then makes it into a nice good format uh, that is good for the eye to see. Next off, we're gonna showcase our LLVM, and to make sure that it's actually generating, we're gonna delete these two files and run it again. You can see the dot format popping up and also the LLVM. The LLVM will be explained by my other partner Biamba, so I'll give now the word to him.
Yeah, we made a code generator class, and it just compares the different types nodes, and based on that, it will generate a different kind of strings and write it to the file that we give to the code generator. So then, if you see, it has include studio, a test function, a main, and in the main function we have variables with pointers, if and else statements, and if we go to the output file, yeah, if you go to the output file, you can indeed see that for example, the main function was declared, the test function too, and also because it was included, you can see that the declare printf and scanf were declared. And yeah, and within the main function, the you can clearly see that the variables are indeed declared, uh, and yeah, the if and else statements, the conditionals are controlled by the labels.
So that was our LLVM. It works as you can see. You can also run the LLVM and generate it for yourself with this command, which is also in our README. So you can see the commands you can use to run either the benchmark or a separate file. Um, this input file is obviously the path to the file you want to run. So if you want to run binary operation, you go to basic testing correct code and then you run the binary operation to test each separate file. Um, the way the benchmark is run is just every C file that's in these files. So if you would like to expand upon it, you can just add the C files inside of here, and then it will also test those files. Um, Aside from the things we've already talked about, if you want to build this project, we also recommend that you pip install the requirements seen in the seen in the README. And um, for further for further things, you can also check the utils, which has some functions that get used in multiple files. So we put it in the util so it's easy to use. I think that was everything for our compilers project. I hope everything was clear, and this is thanks for listening.